This is the video for part 2 of section 7.4, Isomorphisms and Homomorphisms. Now, if two groups G and H are isomorphic, then there exists a bijection F from G to H which preserves the group operations. This means that it will also preserve any properties associated with the group operation. For instance, the property of being abelian is preserved under isomorphism. The proof of this is going to be one of the homework exercises. This means that if G is isomorphic to H and G is abelian, then H is also abelian. Equivalently, if one group is abelian but another is not, then the two groups cannot be isomorphic. For example, the groups S3 and Z6 both have cardinality 6, but are not isomorphic since Z6 is abelian while S3 is not. As another example, the order of an element is preserved under isomorphism. And the proof of this is another homework exercise. This means that if F from G to H is an isomorphism, then for all elements A and G, A and F of A have the same order. We can use this fact to show that two groups are not isomorphic. So here's an example. We want to show that Z4 is not isomorphic to Z2 cross Z2. So the elements in Z4 are the integers mod 4, so they consist of 0, 1, 2, and 3, and they have orders. The order of 0 is 1, order of 1 is 4, the order of 2 is 2, and the order of 3 is also 4. The elements in Z2 cross Z2, which are the ordered pairs with the integers mod 2 as the entries, so that's the ordered pairs 0, 0, 0, 1, 1, 0, and 1, 1, they have the following orders. So the order of 0, 0, the identity element, is 1, and the order of all the other three ordered pairs is 2. So since Z4 has two elements of order 4, but Z2 cross Z2 has none, then the two groups cannot be isomorphic. An isomorphism F from G to G from a group G to itself is called an automorphism of G. For example, let G be a group, and let C be a fixed element of G. We can define F from G to G by F of A is equal to C inverse AC for each element A in G. Then F is an isomorphism, and this is called the inner automorphism of G induced by C. So this is an isomorphism from the group G to itself, and so that's called an automorphism. So to show F is a homomorphism, we need to show for all elements A and B in G, F of AB is equal to F of A times F of B. So suppose A and B are arbitrary elements of G, then F of A, F of B, if we're starting with the right side, this is C inverse AC times C inverse BC, which is, using the associative property, C inverse A times C inverse times BC, and the C inverse in the middle equal the identity, so this will be C inverse ABC, which is equal to F of AB, which is the left side of the identity, and therefore F is a homomorphism. To show that F is surjective, we need to show for all elements G and G there exists an element A in G such that F of A is equal to G. So suppose G is an arbitrary element of G. We need to show there exists an element A in G such that F of A is equal to G. Now the element A must satisfy the condition, the propositional function F of A, which is C inverse AC, has to be equal to G. So multiplying by C on the left and by C inverse on the right in this equation, we obtain A is equal to C inverse. And since C and G are both in G, then A equals C inverse is in G, and F of A is C inverse AC, which is C inverse times C inverse times C, and using the associative law, this is C inverse C times G times C inverse C, and the C inverse C's equal the identity, so this is just going to be G. And this verifies the propositional function, therefore F is surjective. To show F is injective, we need to show for all A and B and G, F of A equals F of B implies A equals B. So suppose A and B are arbitrary elements of G, suppose our hypothesis, f of a is equal to f of b, then C inverse AC is equal to C inverse BC, and multiplying both sides on the left by C and on the right by C inverse, we obtain C times C inverse AC, C inverse, is equal to C, C inverse BC, C inverse. And using the associative law, we obtain this expression, or this equality, and the C inverses all equal the identity, so this reduces to A is equal to B. And therefore F is injective, and thus F is an automorphism. Now, one of the goals of group theory is to characterize groups according to their order and specific properties. So our next theorem provides such a characterization for cyclic groups. So this is theorem 7.19. Let G be a cyclic group, and there's two parts. The first part is if G is infinite, then G is isomorphic to the additive group Z. So if G is an infinite cyclic group, then it's necessarily isomorphic to the additive group Z of integers. And second, if G is a finite group of order n, then G is isomorphic to the additive group Z sub n. So this theorem tells us that if we have cyclic groups, then we basically have two types of cyclic groups. Infinite cyclic groups are isomorphic to the group of integers, and finite cyclic groups are isomorphic to the group Z sub n. So let's look at the proof. So for one, we're going to suppose that G is an infinite cyclic group. That means that G is equal to the cyclic group generated by A for some element A with infinite order. And by theorem 715 part 1, G consists of the elements A to the k for each k in Z, where all of these elements are distinct. That's where the infinite order comes into play. So G is equal to the set A to the k as k ranges over all the integers. Now we need to show that G is isomorphic to Z. To show this, we need to show there exists an isomorphism, f from G to Z. So we'll define f from G to Z by f of a to the ith power is just equal to I for each a to the I in G. And we need to show that f is an isomorphism. To show that f is a homomorphism, we need to show for all elements B and C in G, f of BC is equal to f of B plus f of C. So now note that the operation in G is just multiplication. And so on the left side of this equality, we have BC in the argument for f, and the operation in our codomain Z is just ordinary integer addition. So on the right side of this equality, we have f of b plus f of c, where the plus is just ordinary integer addition. So we'll suppose b and c are arbitrary elements of G. That means that b is equal to a to the I and c is equal to a to the j for some integers I and j. So the elements of G, remember, are just powers of a. Then f of bc is equal to f of a to the I times a to the j, which is equal to f of a to the I plus j, which by definition of our function f is just I plus j, the power, and this is equal to f of b plus f of c. Therefore, f is a homomorphism. Now to show that f is surjective, we need to show for all integers k, there exists a b in G such that f of b is equal to k. So we'll suppose k is an arbitrary integer, and we can choose b equal a to the k power. Then b is in G, and f of b is equal to f of k, a to the k, which is just k. And so this proves that f is surjective. Now to show that f is injective, we need to show for all b and c in G, f of b equals f of c implies b equals c. So we'll suppose b and c are arbitrary elements of G. Then b is equal to a to the I and c is equal to a to the j for some integers I and j. So suppose our hypothesis f of b is equal to f of c. Then f of a to the I is equal to f of a to the j, which implies I equal j according to the definition of our function f. And hence b, which is a to the I, will be equal to a to the j, which is equal to c. And therefore f is injective. and thus F is an isomorphism, so G is isomorphic to Z. Now to prove 2, we'll suppose G is a finite cyclic group of order n, and we need to show that G is isomorphic to the additive group Z sub n. Well, since G is a finite cyclic group of order n, then G is equal to the cyclic group generated by B for some element B with order n. And by theorem 715 part 2, G is going to consist of the powers of B, B to the 0, B to the 1, B to the 2, up to B to the n minus 1. And we need to show that G is isomorphic to Z sub n. So using the congruence class notation, we can write Z sub n as the congruence class of 0, the congruence class of 1, congruence class of 2, all the way up to the congruence class of n minus 1. And let's define G from little g from G to Z sub n by G of B to the I power will be the congruence class of I for each integer I from 0 up to n minus 1. And we need to show then that G is an isomorphism. To show G is a homomorphism, we need to show for all C and D in G, G of CD is equal to G of C plus G of D. So suppose C and D are arbitrary elements of G, then C is equal to B to the I and D is equal to B to the J for some integers I and J. Then G CD is equal to G B to the I, B to the J, which is equal to G of B to the I plus J, which by definition of our function G is the congruence class of I plus J. And we know that when you add two congruence classes, you'll get the congruence class of the sum, so this will be the congruence class of I plus the class of J, which is equal to G of C plus G of D. And therefore G is a homomorphism. To show G is surjective, we need to show for all congruence classes K in Z sub n, there exists a C in G such that G of C is equal to the class of K. So suppose the congruence class of K is an arbitrary element of Z sub n, and we can choose C to be B to the K, then C is in G, and G of C is equal to G of B to the K, which is the congruence class of K, and this shows that G is surjective. Next, to show G is injective, we need to show for all C and D in G, G of C is equal to G of D, implies C equals D. So we'll suppose C and D are arbitrary elements of G, then C is equal to B to the I and D is equal to B to the J for some integers I and J, and we can assume that I and J are between 0 and n minus 1. Remember now, G consists of the powers of B, where the powers are all between 0 and n minus 1. So let's suppose our hypothesis G of C is equal to G of D. Then G of B to the I is equal to G of B to the J. That's what C and D are. So that means that the congruence class of I is equal to the congruence class of J. That's how our function is defined. And this implies I is congruent to J mod n. And since I and J are between 0 and n minus 1, the only way that I can be congruent to J mod n is if I and J are equal. So this implies that I equals J, and hence C equals B to the I equals B to the J equals D. And therefore G is injective. And so this shows that G is an isomorphism, so G, the group G, is isomorphic to Z sub n. And this completes the proof of the theorem. For an example, let's let G be Q star be the multiplicative group of non-zero rational numbers. Then the cyclic subgroup generated by 2 will be the powers of the integer powers of 2. So it'll be the set of 2 to the k as k ranges over all integers. And you can write that out. So this will be ... 1/16, 1/8, 1/4, 1/2, 1, 2, 4, 8, 16, ... Now the theorem implies that since this is an infinite cyclic group, that the cyclic subgroup generated by 2 is isomorphic to the additive group Z. For another example, we can show that we can use the theorem to show that U sub 5 is isomorphic to U sub 10. Okay, so these groups are U sub 5 consists of 1, 2, 3, and 4, and U sub 10 is 1, 3, 7, and 9. Okay, so U sub 5, these are the integers in Z sub 5 that are invertible, so those will be 1, 2, 3, and 4, and U sub 10, these are the units in Z sub 10, so the integers in Z sub 10 that are invertible. And again, the elements of U sub n are going to be all the integers mod n that are relatively prime to n. Okay, now note that in U sub 5, if I look at the powers of 2, we'll obtain 2 squared is 4, 2 cubed is 8, mod 5 is 3, and 2 to the 4th is 16, but mod 5, that's 1. So that tells us that the order of 2 is 4. The smallest power of 2, which equals the identity 1, is 4. And therefore, U sub 5 will be the cyclic subgroup generated by 2. So taking the powers of 2, we obtain all the elements of U sub 5. In U sub 10, if I look at the powers of 3, 3 squared is 9, 3 cubed is 27, but mod 10, that's 7, and 3 to the 4th is 81, but mod 10 is 1. So this tells me that the order of 3 is 4. And therefore U sub 10 will be equal to the cyclic subgroup generated by 3, so U10 is cyclic, generated by 3. Okay, so since both groups are cyclic of order 4, then the theorem implies that both U sub 5 and U sub 10 are isomorphic to Z4. Well, if U5 and U10 are both isomorphic to Z4, that implies that they're isomorphic to each other. The next theorem shows that every group is essentially equivalent to a group of permutations. And this is theorem 7.21, which is called Cayley's theorem. And this just tells us that every group G is isomorphic to a group of permutations, exactly what I just said. Okay, to prove this, we're going to suppose G is an arbitrary group, and we want to find a group, we'll call it G bar, of permutations that is isomorphic to G. To do this, we'll use G to construct the group G bar. So for each element A in G, we're going to define a function. This is phi sub A from G to G by phi sub A of G is A times G for each G in G. So for each element A in our group G, we're defining a function phi sub A from G to itself. And we want to show that for each A in G, phi sub A is a bijection. To show that F is a bijection, we need to show it's injective and surjective. So to show it's surjective, we need to show for all H in G, there exists a G in G such that phi sub A of G is equal to H. So we'll suppose H is an arbitrary element of G, and we need to show there exists a G in G such that phi sub A of G is equal to H. So we'll do this with a two-column proof. So we need to find G, and we need to verify that G satisfies our conditions. The domain G must belong to G, and our propositional function, phi sub A of G, must be equal to H. So G must satisfy the propositional function, which is phi sub A of G equals AG is equal to H. So to find G, we can multiply by A inverse on the left in this equation, and we'll obtain G is equal to A inverse H. So we've got our G, and since A and H are both in G, then G equals A inverse H belongs to G also. And the propositional function holds since phi sub A of G is just AG, which will be A times A inverse H, and the A and the A inverse will cancel each other, they'll equal the identity, so this will leave us H. And therefore phi sub A is surjective. Now to show that phi sub A is injective, we need to show for all G and H and G, phi sub A of G equals phi sub A of H implies G equals H. So suppose G and H are arbitrary elements of G. Suppose our hypothesis phi sub A of G equals phi sub A of H. Then AG is equal to AH by the definition of our function, which implies by canceling A on the left that G is equal to H. So this shows that phi sub A is injective and thus is a bijection. So these functions phi sub A that we've defined are bijections. Now they're not homomorphisms. So they're not going to be isomorphisms, they're just bijections. Now, since phi sub A is a bijection from the group G to itself, we can view phi sub A as a permutation of the elements of G. Basically, if you have a bijection from a set to itself, it's permuting the elements. It's mapping each element to another element in the group, and it's a one-to-one correspondence, so that will be a permutation of the elements of the set. Now let G bar be the set of all these permutations phi sub A as A ranges over the elements in G. So we're going to define a group G bar that we want to show as isomorphic to G. So now we've got this set G bar. So it's a set of all these functions phi sub A as A ranges over the elements of G. Now we want to show that this G bar is actually a group under the operation of function composition. So to show this, we need to verify the four group axioms. Well, before doing this, we want to first show for any A, B, and G, phi sub A composed with phi sub B is equal to phi sub AB. So this is an identity for these bijections. To show this, let's suppose that A and B and G are arbitrary. And to prove the identity, we need to show that for any G and G, phi sub A composed with phi sub B of G is equal to phi sub AB of G. So phi sub A, phi sub B, and phi sub AB are all functions. So to show that two functions are equal, to show that the composition phi sub A composed with phi sub B is equal to phi sub AB, we have to show that when you apply them to any element in their domain, we obtain the same result. So let's suppose that G and G is arbitrary. Then our left side, phi sub A composed with phi sub B of G, is equal to, by definition of the composition, this is just phi sub A of phi sub B of G. And phi sub B of G is BG. That's how phi sub B is defined. And then phi sub A of BG is A times BG. That's how phi sub A is defined. And using the associative law, this is just going to be AB quantity times G, which is equal to phi sub AB of G. So this proves the identity, phi sub A composed with phi sub B equals phi sub AB. And now we can use this identity to go ahead and verify the group axioms. So the identity implies that the composition of two mappings in G bar, phi sub A and phi sub B, is another mapping in G bar, phi sub AB. So this tells us that G bar satisfies our first axiom, G1, which is closure. Now the associative law G2 holds since function composition in general is associative. So now we have to prove G3, the existence of an identity element. Well, let's let E be the identity element in the original group G. Then phi sub E will belong to G bar, and for any element A in G, phi sub E composed with phi sub A is equal to phi sub EA. That's using our identity, which is just phi sub A. That's since EA is equal to A, because E is the identity element in G. And phi sub A composed with phi sub E is equal to phi sub AE, which is equal to phi sub A. So this tells us that this phi sub E behaves like an identity element in G bar for these permutations. So G bar satisfies G3. To prove G4, the existence of inverse elements, let's suppose that A and G is arbitrary. Then phi sub A composed with phi sub A inverse will be phi sub A inverse, which is phi sub E, and that's our identity element in G bar. And phi sub A inverse composed with phi sub A is equal to phi sub A inverse A, which is phi sub E, again the identity element in G bar. And this shows that the inverse of phi sub A is equal to phi sub A inverse. So this tells us that every element phi sub A in G bar has an inverse element. It's given by phi sub A inverse. So G bar satisfies our fourth axiom, G4. And thus G bar is a group. So now we've got this group G bar consisting of permutations of the original group G. And we next want to show that G is isomorphic to G bar. And that was our original goal in the theorem, was to find a group of permutations that G is isomorphic to. So we are going to define f from G to G bar by f of a is equal to phi sub a for each element a and G. And we need to show that f is an isomorphism. So we first show that f is a homomorphism, and to do this we need to show for all a and b and G, f of ab is equal to f of a composed with f of b. So note again that the operation in G bar is function composition, so that's what we have on the right side of this equality. So suppose a and b are arbitrary elements of G, then f of ab equals phi of phi sub ab, which by our identity is phi sub a composed with phi sub b, which is equal to f of a composed with f of b. And therefore, f is a homomorphism. Since by definition G bar consists of the images f of a equal phi sub a for each a and G, that tells us that the image of f will be G bar, which means that f is surjective. And then finally, to show that f is injective, we need to show for all a, b, and G, f of a equals f of b implies a equals b. So suppose a and b are arbitrary elements of G, suppose our hypothesis, f of a equals f of b, then phi sub a is equal to phi sub b by the definition of our function f. And applying each of these functions to e, we obtain phi sub a of e equals phi sub b of e. And by definition, this is ae equals be, which reduces to a equals b. So this shows that f is injective, and thus f is an isomorphism, so G is isomorphic to G bar. So we've shown that there exists a group of permutations of G that G is isomorphic to. And this completes the proof of the theorem. Now for any group G, we can let A of G denote the group of permutations of G, that is, the group of bijective functions from G to itself. In the theorem, the group G bar that we've constructed is a subgroup of A of G. Now, in the case that G is a finite group of order n, then A of G, the group of permutations from G to itself, will be isomorphic to S sub n. This will be a group of permutations of n elements, so it will be isomorphic to S sub n. So G bar will be isomorphic to a subgroup of S sub n. And the following corollary follows from this observation. So this is corollary 7.22. And this says that every finite group G of order n is isomorphic to a subgroup of the symmetric group S sub n. Now, a homomorphism from a group G to a group of permutations is called a representation of G, and G is said to be represented by a group of permutations. Now, the homomorphism F from G to G bar in Cayley's theorem is called the left regular representation of G. Okay. Now, from a theoretical point of view, Cayley's theorem says that the study of groups can be reduced to the study of permutation groups. So the theorem tells us that every group is isomorphic to a subgroup of permutations, or a group of permutations. So if you want to study groups, essentially what it tells you is you only need to study permutation groups. So instead of studying all the different types of groups, each with their own operation, we could just study permutation groups under the operation of composition. However, this viewpoint is usually not very efficient, since the groups will be subgroups of very large permutation groups. For instance, corollary 7.22 tells us that a finite group G of order 12 will be isomorphic to a subgroup of S12. Well, S12 has order 12 factorial, which works out to 479,001,600. So instead of examining the properties of a group of order 12, we would have to infer its properties by investigating subgroups in S12, which is a much, much larger group. So this is generally not a very efficient method for studying groups, and so it's not really used very often. Okay, so this finishes up the part 2 of section 7.4.